So this is the final project presentation for our group in the optimization class, Mechanical Engineering 575. We are working on specifically a fault repair system for an AUV that uses discrete action planning. My name is Devon Webb.
And I'm Kalin.
So just to start off, for a little background information, what an AUV is it stands for Autonomous Underwater Vehicle. And these are robots that are designed to do things like survey the ocean floor or ships, reefs, do a lot of surveying missions. And as such, they have a lot of different sensors on board, both to do surveying, but also to remain autonomous. They have sensors like cameras, IMUs, sonars, and then they've got other subsystems like thrusters, computers, lights. There's a lot of different components included in these things. And as such, a lot of those components can break during operation. Now, for these systems to be fully autonomous, they need to be able to handle these malfunctions as they come up. Currently, when these AUVs break, most people who build these AUVs program them to just abandon whatever mission they're going on to save the AUV, which is good because it saves the AUV, but it kind of takes away from some of the automation. Ideally, what we would want is for these robots to be able to diagnose and repair themselves if applicable. And so that's what we were working on, is working on a repair and diagnostic system for these types of robots, specifically the repair system. So I'm just going to go over a quick flow chart of how this works. Typically what happens is there's a diagnostic system that produces it goes through the robot and figures out which systems might need to be repaired, if any. Given that some systems do need to be repaired, it'll send over LCM, which is similar to ROS. It's just a communication protocol in between robotic systems. This diagnostic system will send over a list of systems that need to be repaired to some repair system, which includes a planner, which is this. So this section, which determines which actions will result in those systems being repaired. And then send those repair actions to some repair system that can carry out those actions. And so the section that we were working on is this planner section, which takes as inputs the systems that need to be repaired and then outputs a list of actions to complete that, specifically an optimal list of actions. So the smallest number of actions that can be done that will result in those systems being repaired. And how GraphPlan works, the reason why we picked it, I guess first off, is because it's straightforward, meaning that it's fairly easy to understand when you break it down into pieces, especially for a discrete optimizer. It breaks down into a few basic pieces. So it breaks down into some states. So in our instance, the states will be the systems on the robot, which ones are working and which ones aren't. So like in this example to our right, A and B and C might be different systems on the robot. A is a working robot, B is a working system, B not is probably a broken system. So we'll have some initial set of states and our goal set of states, which for our instance is going to be all the states working at the same time. GraphPlan also includes a set of actions. So in this instance, these X's and Y's are the actions in this example, and each of these actions have preconditions and desired effects. So in this graph, we have lines that go to these actions that are the preconditions, and then the desired effect, which would be given that A and B exist, this action will result in A naught. And then the solution that's included in this graph plan is just a list of actions. And so the idea is that it will optimize this, find an optimal solution, which is just the list of actions that will reach the goal within the fewest or a minimum number of steps.
Perfect. So just like Devon was talking about, the algorithm can be broken into essentially these 3 different steps. So initially we have the graph expansion. So from your initial state and any state at any level of the graph, you take all of the possible actions at that point and add them to the graph, as well as their outcomes. And those outcomes then form the next level of the graph. Then you, at each level of the graph, want to check to see if your goal is within those states. And if the goal is, you can begin looking for a solution. If the goal is not present in that level of the graph, then you continue to expand the graph until the solution becomes possible. And lastly, you have the solution search. So this is the part that isn't very easily shown by the graph that Devon was showing in the previous slide. But essentially, working from the top level of the graph, you then work backwards, moving through all the different actions and states, identifying which ones of them can and cannot be performed together, or in other words, which ones are mutually exclusive from one another. And then a solution is found when you have traced a path from the last level of the graph down to the initial level of the graph. And if all of the actions that you have taken along that path are not mutually exclusive, then you have found a solution. So in our case, we have a problem that Devon briefly talked about. We're using a hovering autonomous underwater vehicle that is equipped with some hardware and software systems that all work together to ensure the autonomous operation of that vehicle. So we have the camera, an inertial measurement unit, some thrusters, and then some image processing localization software, a trigger signal that's sent to those different software and hardware components, and then also a controller to enable this vehicle to move by itself. And from these, so these are our states, essentially, and each of those is either functioning or not functioning, and that makes up the entire state, possible set of states. And all of the hardware can be reset, so those are the possible actions that relate to hardware, and then all of the software can be either enabled or disabled, so those are the possible actions. And here's actually a snippet from our algorithm where we built, where we kind of define our system in the code. And so these are all the different actions, resetting the camera, and then here are all the preconditions. So the camera has to be disabled, the PPS has to be disabled, and the localization or the SAM has to be disabled. And then for each of these hardware and software systems, we define all of the possible actions and their preconditions. And then using this system, GraphPlan is able to then work with an initial state that is provided and provide a solution, which is a set of these actions that will reach the goal state. And the goal state in our case is to have everything operational. And so here, some of the results. So the solution is output to be very understandable and to be taken at different levels. And so, like I talked about before, some actions can be mutually exclusive. In other words, they can't be performed simultaneously, but other ones aren't mutually exclusive and can be performed simultaneously. So here's an example input and output from our algorithm. And so we started it with this initial state where the camera wasn't working, the IMU wasn't working, neither was OpenCV or the PPS or the thrusters. The only things that were working were SAM and the controller. And then using that system that we defined and showed on the previous slide, then it was able to work through the graph and provide this solution, where at the first level, the vehicle will disable the SAM and then enable the thrusters. And then at the second level, it will enable the camera and the IMU. At the third level, it will enable the PPS signal. And then at the fourth, OpenCV. And finally, it will re-enable SAM and have everything back in an operational state. And so also one of the interesting things, we wanted to check to see if this algorithm was fast enough to be used online, as when a vehicle detects a problem, you really don't want it to be out of commission for very long, especially as once you've disabled systems, you've got a vehicle that's floating in the water, and you could lose track of it, and you really don't want that. So for our problem, we had 8 design variables, which led to a total of 256 possible initial states for our algorithm. And then, as I pointed out, the design variables already, the constraints are represented by those preconditions for the actions. And so we ran our algorithm for all of the 256 possible initial inputs. And in order to provide a solution for all 256 of those, it took 0.06 seconds, well, 0.07. So not only was it able to run one very quickly, but it was able to run all of them extremely quickly. The longest time actually that it took to perform any one of those individual solutions, to find any of those individual solutions, was 1 millisecond. And so this is definitely fast enough to run online and could very easily be implemented on a robotic system and run without any concern for losing the vehicle or encountering other problems as a result of trying to solve this dilemma. And so why is this problem in our algorithm significant? So we talked about having it on one robot, and while that is extremely useful to be able to have one robot that can go around, perform a mission, and diagnose and repair any issues that arise during that mission. One of the great things about this algorithm is that it's extremely easy to scale it to even multiple systems. So one of the interesting areas of research right now is in multi-agent systems where you've got multiple robots working together and communicating with one another. And with this algorithm, you could actually define a system that has interactions between those different vehicles where if something goes wrong with one, another one could go and repair that vehicle if that vehicle is not able to repair itself. And so deploying a fleet of these vehicles, you could also have this algorithm running on any one of them. And like here, this boat at the top is working as kind of a ground or a base station. And so that base station could be what coordinates the efforts of all of these vehicles if anything were to ever go wrong. So this algorithm is really nice. It is able to be easily used and expanded and applied to any robotic system, just so long as all of the actions are simply defined by a list of their preconditions and their effects, and under the assumption that those effects will actually result. But yeah, that's our presentation and our project. Thank you very much.